the first one's true. Long phases, there's iterations, but they're much longer than spiral. Second one is true. There's no working code at the end, but they do iterations. They're just a lot slower there. Waterfall and spiral have architecture design phases, but you cannot incorporate architecture in Agile lifestyle. This is one of the criticisms of Agile, is you just jump in and write code, are you really going to have a good architecture? And in fact, a guy named Jeff Beck, who's one of the guys who signed the Agile Manifesto, was asked this in his talk. Doesn't it mean if you build software that way that you're not going to have good architecture in it? And he says, isn't it possible? Somebody said, yeah. He said, yes. Not only is it possible, it's going to happen. What you have to do is refactor your code to put good architecture in. So but he would argue it's not incompatible, but you're going to have to work at this when we do the refactoring. The thing about not using written requirements is the user stories are written. As you'll do it yourself, you'll write these user stories in 3x5 cards. You use 3x5 cards to make it easy for the non-technical customer to understand that. But there is a written piece. You'll use those cards. It's just a little bit less formal than is done. So what I was shooting for was the red one, the third option. But the main idea is to see if you understand it. Any questions about that? Questions? You'll see the user stories soon. All right, next up, testing and formal methods. Testing is a big part of this course. The fact that you will write tests before you write code is amazing to faculty at other institutions, but I've been doing it. So there's two related ideas, verification and validation. They sound like synonyms in a thesaurus. But by verification, you mean, did you build the thing right? That is, did you meet the specifications? Validation is, did you build the right thing? That is it what the customer wants? So not surprisingly, hardware focuses on verification. Did you meet the spec that Intel write? Where software is validation. Even if you met it, is that what the customer wanted? So that's verification versus validation. And then two of the options here are testing and formal methods. So in testing, we cannot do exhaustive testing. So an example that's there in the margin of the book, suppose you could do a test in 1 nanosecond, which would be amazing, and you had one 64-bit variable. How long would that take? 2 to the 64 nanoseconds. Well, there's 2 to the 30th nanoseconds in a second, so that is 2 to the 32 seconds. It turns out there's about 32 million seconds in a year, so that's 2 to the 25th. So that we're left with 2 to the 34th divided by 2 to the 25th, that leaves 2 to the 9th, 500 years, 512 years. It would take 500 years if you had one 64-bit variable, and you could do a testing in a nanosecond if you tried to do exhaustive. So you can't do that. So what we do is we divide and conquer. We do different tests at different phases, and there's a lot of names in here about testing, because testing is such an important part of what we do. The base thing is called unit testing. That's testing to see if a single method does what's expected. Sometimes people use the name module or functional testing to test across individual units, like across classes versus within a class. Integration testing is to try and see if a bunch of modules communicate correctly, so it's a more narrow interface. And each time you add one of these things, you're assuming the one below does that work. And finally, at the top is system or acceptance testing. Does the whole program meet what the customer wants it to do? So those are the names of testing. Other things that happen that you hear about testing is coverage, which is the percentage of the paths that are tested. So when there's branching statements, are all the paths exercised by the test? That's coverage. Regression testing, since you're going to be building software over time and iterating it, did the latest thing you add break something before? So you want to keep doing a regression test, trying all the tests you've ever done over it again. And there's even a phrase called continuous integration testing, that as you build software in the background using the cloud, you'll be running all the old tests all the time, so you immediately find out if you broke something. As we said, we're emphasizing test-driven design and Agile, that you're writing the test before you had the code you wish you had. So the tests are going to drive the code. This is by Edgar Deisker. Program testing can show the presence of bugs but never show their absence, right? So the problem is you can find bugs there, but you can't prove that they're not there. And that led to an attempt to do formal methods. And basically, you get a formal specification, tying like in the waterfall model, and they prove that program behavior follows that specification. You could do it by hand, which is incredibly tedious. It was so tedious, it's hard to do. People quickly abandoned it. So big advances in automatic theorem proving using inference and logic axioms, a specification language to try and prove from scratch. That was tried for a while, but a more popular thing today is what's called model checking. You have limited properties that you exhaustively search by doing symbolic execution and look at all possible states, and that's another way. So these formal methods, as they're called, unfortunately, even as fast as computers are today, are incredibly expensive. So they only get used today if you've got something really important, it's not going to change, it's expensive to repair, and it's not too big. So it is used today in hardware systems that's used for network protocols, safety critical software. But and to give you an idea how expensive it is, the biggest thing that anybody's tried to do is 10,000 lines of code of a simple operating system kernel. And that costs $500 per line of code. Putting that in perspective, NASA software, like flying the Curiosity, that's pretty expensive. That's $80 a line of code. So this is incredibly expensive. And it doesn't really work with rapidly changing software, right? You change the software, you got to go through that all again. So it's not something we're going to use. We're going to do software that changes fast, easy to repair, easy to test. So we're not going to do formal methods anymore, but there's plenty of classes you can learn about that. Okay. All right, so time for that cards again. Which statement is not true about testing? With better test coverage, you're more likely to catch faults. While difficult to achieve, 100% test coverage ensures design reliability. Each higher level test delegates more detailed testing to lower levels, and unit testing works within a single class and module across classes. Okay, which one is false?